Well, last time we started discussing the demodulation of FM waveforms. And the first thing we saw was a direct method. By first taking the FM signal and converting it to an AM signal through the use of a differentiator. And then as the differentiator output is proportional to the magnitude, which is in terms of the input signal, the message signal, M of t, we can then use an envelope detector in principle to demodulate. However, this requires a balanced discriminator, and it may run into problems in terms of noise immunity, especially in the case of low signal to noise ratio. We have a threshold effect in FM, which we will study later, that this structure is very prone to. Therefore, the more useful technique for demodulating FM waveforms is to use a feedback loop. The main ingredients of a is to use a voltage controlled oscillator in the feedback loop, to which we feed the demodulated signal. So here is the principle. So at the structure that you're seeing here is actually a phase lock loop. Phase lock loop, abbreviated as PLL. And here is how it works. So the input to the VCO is V of t, and what the VCO does is, in the absence of any input, it produces a sinusoid at frequency FC. Okay, but when the input signal is V of t, it will produce a signal whose instantaneous sinusoid, whose instantaneous frequency is FC plus a multiple of V of t. All right. So now, in this case, so basically when it's tuned to FC, okay, in the absence of an input control voltage, it will produce FC. In the presence of a control voltage, let's call it control voltage, it will produce this instantaneous frequency. So let's see what happens. This is the output. Okay. It's basically an FM modulated waveform, essentially, a little bit different. Okay, phi u of t is the phase here at the output of the VCO, which is 2 pi kV integral from 0 to t v of tau d tau. We are assuming a boundary condition that v of 0 is 0. Okay. So this is fed into a phase comparator. What a phase comparator is basically a mixer followed by a low pass filter. I mean, followed by filtering that will eliminate components centered at FC. Okay, so the result of this phase comparator is an error signal when we multiply this waveform, basically, cosine 2 pi of ct plus phi of t, plus this waveform, sine 2 pi of ct plus phi v, and low pass filter, the result we obtain is such a signal. Now, provided that the feedback loop is locked, in other words, provided that this difference is small, we will approximate the sign of the error. So let's call this phi e of t. We will approximate sine phi e of t as phi e of t. And in that case, we will be able to make a linear approximation for this feedback loop. Okay. So this is, let me write it down. This condition is when the PLL is in lock. So suppose it's in lock, suppose it's working, then phi E is going to be small, and we can make this approximation. Okay, so phi E is coming in, and V is going out. Okay, so we will use a linearized model for this, where phi E is coming in, and it is filtered by some filter such that the result is V of t, and we want the V of t to be the demodulated signal or proportional to it. So basically we want V of t to be proportional to M of t. So what should the loop filter be such that this is achieved? Let's do the analysis of this feedback loop. Now, phi of t clearly is the difference between phi and phi v. What is phi v? Phi v is obtained by integrating v. Okay. Let's differentiate this equation, d phi by dt, d phi e by dt, plus 2 pi kv v of t. Okay, notice that we have zero initial condition, is equal to the derivative of phi. All right. So now let's put in the loop filter. Let's express V of t as the convolution of phi e with the loop filter impulse response. Okay. And then take the Fourier transform of this integral differential equation. What do we get? 2 pi jf phi e of f plus 2 pi kv phi e of f g of f equals j2 pi f phi of f. Now we can obtain the Fourier transform of phi e in terms of Fourier transform of phi f and the filter this way. Now, if the filter is such that, this magnitude, the magnitude of this term, is small with respect to 1 within the frequencies of interest. What are those frequencies? The frequencies in phi e and the frequencies in phi f are basically the frequency band at which the message is appreciable. Meaning, so we're talking about frequencies within W, the message bandwidth. For frequencies within the message bandwidth, if the magnitude of this term is much larger than 1, if I said smaller, I'm sorry, it's a correction. If it's much larger than 1, then we can ignore the 1. So basically, approximately, this is G of the relationship between V and phi is given by G canceling. Therefore, we have J2 pi f over 2 pi kV phi of f. Okay, so going back to time domain, we have V of t equals 1 over 2 pi kV d by dt phi. What derivative of phi is kf m of t, so we are done. Okay, so when the PLL is operating at lock position and the phase difference is small, the feedback circuit results in the demodulation of the FM waveform. Any questions? Now there's another similar structure with the same operating principle that you will see as the FM feedback demodulator. And that also, this diagram exists in your textbook. So the way this one is designed is, again, there's a VCO in the feedback loop, which takes the output signal, just like the previous system, takes the output signal, which is V of t, preferably, ideally proportional to M of t. And the VCO result is mixed with the incoming waveform and then passed through a bandpass filter. This is then fed through the discriminator and low-pass filter. If you do the linearized analysis, it is very similar to the PLL. This is also essentially another PLL design. So the critical component is the discriminator. Here, remember, we were using it without feedback in direct FM demodulation. What is the reason of the feedback for the feedback loop? The reason for the feedback loop is immunity against noise. So this has better noise performance than the direct demodulation method. And when we come to noise analysis later on, we will revisit this. Okay.
Hocam, bu yöntemin drawback'i ne peki? Mesajın sinyalinin amplitüdünün azalması mı? Çıkışta.
You need a VCO, which means you need a sophisticated oscillator, and good quality oscillator. Any other questions? So in the remainder of our time, I would like to work out a few examples, maybe one or two. Okay, so let's do some example problems. Suppose you're given this signal, U of t equals 5 cosine 2 pi 10 to the 4 t plus 4 times 10 to the minus 3 sine 2 pi and 10 to the 3 t. Okay. So my first question to you is, do you recognize this as a certain modulation type? Well, of course you do. What is it? So this is an FM modulated waveform, right? With a what kind of signal? Single tone. Okay. So is it narrowband FM or wideband FM? How do we check? Where's the beta? All right, so beta here is by definition 4 times 10 to the minus 3, oops, which is much less than 1, right? So this is a narrowband FM waveform. Agreed? Okay, so now the question is, how do you modify U of t through using certain circuit elements like frequency multipliers, local oscillators, filters, okay, to obtain a wideband FM signal, okay, with the following properties. Carrier frequency, 2.4 times, let's see, 240 megahertz. Okay. Peak frequency deviation, 100 kilohertz. How do you achieve this?
Using an angle modulator.
Right. I mean, design a system that takes, so basically, we already have M of t coming in, and this has been narrowband FM modulated. Oops. With center frequency. What is the center frequency here? Carrier, the first carrier.
10 kilohertz.
10 kilohertz. Okay. And we have at the output U of t. Okay. Now we want to do something to U of t. We want to do a number of things to U of t, such that we obtain a signal at the output with Fc equals 240 megahertz and frequency deviation 100 kilohertz. How do we do this? Sure. Yeah, right. That could have been a phase modulated waveform as well. We commonly pick FM. You know, phase modulation is also a valid angle modulation type, but we saw that its bandwidth increase is faster with the input signals bandwidth. So for that reason, and several other reasons possibly, FM is usually preferred. While we define phase modulation, we often, most of the time, we focus on FM. Right.
Hocam, beta çok küçük değil mi bunu yapmak için?
Well, it is small, but why should it be too small to do this? Why can't? I mean, it's possible to go. I mean, so basically, you're observing that we need to increase the beta. What do we need to increase the beta to?
Max deviation over the frequency, center frequency.
So?
About 10.
So we basically, maybe we can go from the following. We are coming from a delta F. So basically delta F here, delta F narrowband is equal to what? Let's compute it. So beta, so the original beta is 0. I forget. What is the original beta? 4 times 10 to the minus 3. 0.004, right? And so beta is delta F over FM, right? So delta F narrowband FM is 4 times
40
times FM. What is the center frequency? 10 kilohertz, right? 10 times 10 to the 3, 40, right? Oh, I'm sorry. I used the wrong frequency here. What is FM? 10 to the 3. Let's go back here. Right. FM is 10 to the 3. So 10 to the 3. So delta F is 4 hertz. Very small instead, indeed. Okay, so we are asked to increase the delta F to 100 kilohertz. As we saw the math during the last lecture, if we use a frequency multiplier here, appropriate frequency multiplier, we will be able to increase delta F directly by whatever the frequency multiplication value is. So delta F over delta F narrowband is 100 kilohertz over 4 hertz. And what is the ratio?
25,000.
Pretty large, right? I mean, theoretically, it is possible, I guess. It may not be, the numbers may not be very practical at the moment. Okay, 25 times 10 to the 3. Okay, so now what do we do? What happened after the frequency multiplication? What kind of signal do we have? The center frequency has been moved to, right, 25 times 10 to the 3 times 10 times 10 to the 3, right? 250 megahertz. And the delta F is at the desired value. Delta F has been fixed. However, FC has not been brought to the right location. What can we do to bring it to the right value?
We can use a local oscillator with 10 megahertz frequency.
Yeah, we can get a local oscillator, or it's usually drawn like a circle. A local oscillator frequency what?
10 megahertz.
10 megahertz. Okay, and then use a bandpass filter appropriately placed. We're done. Okay. What is the beta at the output? What do you do to compute it? Delta F over FM. So basically delta F over FM again, right? And 100 kilohertz divided by 10 to the 3, right? Which is what? 10 to the 3 hertz, right? So 100. I mean, this is a little bit too wideband than normal, maybe, but for the sake of example, it works. For practical concerns, probably we would start with a larger beta to start with, or use multiple stages. Any other questions? Any questions? Let's switch gears a little bit and work out an example. Sort of going back to earlier lectures. Consider the modulated waveform. X of t equals 500 sync 500 pi t times cosine 5,500 pi t. Right. Now, can you identify this? What modulation this is? I don't know. Maybe take a look at the frequency domain expression. Okay. Suppose we look at the. I'm just going to use W. So, well, 1/2. Well, this is a sink, okay? So we will have two shifted rect functions in the frequency domain. 1/2, and the 1/2 scaling comes from the Fourier transform of the cosine. Rect W minus 5,500 pi over 1,000 pi, okay, plus rect W plus 5,500 pi divided by 1,000. So let's sketch this. Let's see how it looks. So this is x of W as a function of W. And this is 5,500 pi, negative 5,500 pi. And what is the bandwidth of the rect?
Thousand pi.
Excuse me?
1,000 pi.
Right. And how is it going to look?
Hocam, instead of 5,500
Mhm.
pi, shouldn't we use 5,500 over 2?
Let's see. Why?
Because the cosine frequency is.
Oh, you're right. No. Right, exactly. You got me confused. We're working with radians here.
Okay.
Okay. You got me confused for a moment there. Okay, so let's see. How is it going to look? Where are they centered? Like this? Like this? No? So, oops. What is the width? Okay. So what kind of, if the carrier signal, oh, I didn't give you the carrier. If the carrier is 500, so basically carrier frequency, or if the carrier is, wait, C of t equals cosine 5,000 pi t. Okay. Then what is the modulation? Right, upper sideband, right? So notice that the carrier frequency Xc is here. So this is upper sideband modulation. Now, the answer is upper sideband. How do you demodulate it? How would you demodulate it? Take x of t and what? Well, all you need to do is really bring it to the baseband by a mixer and then filter it. So twice cosine 5,000 pi t. Okay, and then low pass filter, and the result will be empty. Any questions?